Hello there. In this video we're going to derive the formula for an area of a circle. So recall that the distance between the center and the circumference in any direction is going to be denoted by r, which is going to be the radius. And as we all should know by now, the area of a circle is going to be pi r squared. So we're going to use a trig substitution method in order to derive this expression. So if you're not familiar with integration or trig substitution, definitely refresh that before moving on, or you can maybe pick up on the skills in this video directly. Alright, so let us consider a coordinate plane so we can sort of have a function to sort of integrate around. Let this be x and let this be the y-axis, and let's consider a circle. So as we should know, the equation of a circle is given by x squared plus y squared is equal to r squared. So if we solve this equation for y, for example, so we can get a function of x, y is going to be equal to the square root of r squared minus x squared. And this is usually plus or minus. Plus is going to be the top half, minus is going to be the bottom half. So that means if we want to sort of find the area of the circle, we need to only consider the top half, since that is only going to be a function, and then we can multiply that area by 2 to get the final result. So this function f of x is going to be equal to the square root of r squared minus x squared, and integrating from minus r to r should give us half of the area of the circle. So that's going to be pretty much the strategy here. So let's write that down. So that means area must be equal to 2 times the integral from minus r to r of the function square root of r squared minus x squared dx. Alright, so now let's go through the process and hope that this comes out to r squared. Alright, so we're going to begin by using a substitution. We're going to be letting x be equal to r times sine of theta. You're going to want to use this trig substitution every time you have a variable by itself that is located underneath a square root with some difference. If it's a plus, you may want to use like tangent or something similar to that. So if x is equal to r sine theta, then that means the derivative of x with respect to theta is going to be equal to r cosine theta d theta. Alright, so that gives us something to sort of deal with this dx term. So let's also worry about the limits here. So that's the first observation. The second, so if x is equal to minus r, then that means minus r, so we're using this equation here, is going to be equal to r sine theta. So divide both sides by r, assuming that r is non-zero, so that means negative 1 is equal to sine theta. So that means theta must be equal to the arc sine of minus 1. So remember that arc sine is bounded in the region minus pi over 2 to pi over 2. So arc sine of negative 1 is going to be negative pi over 2. And similar, you can find the other value. So if x is equal to positive r, then theta is going to be equal to positive pi over 2. Alright, so let's just, include those details here. So that means a is going to be equal to 2 times the integral of minus pi over 2 to pi over 2 times the square root of r squared minus x squared times dx. And dx here is going to be r cosine theta d theta. Now, this is an integral with respect to theta, so all our x's need to be transformed here. So let's sort of figure out what to do with that. So if x is equal to r sine theta, that means the square root of r squared minus, so x is going to be r squared sine squared theta. So we can factor out an r squared out of this, so that's going to be equal to r times the square root of 1 minus sine squared theta, which is going to be equal to r times the square root of cosine squared theta, which is going to be equal to r cosine theta. So this is just some scratch work here. So what does that mean? So we go back to our integral representation. So a is going to be equal to 2 times the integral of minus pi over 2 to pi over 2. We can replace this square root term with this r cosine theta. So we have r cosine theta times this r cosine theta d theta term that we derive from the differential of x. Alright, so r and r are both constants, so we can factor both of them out of the integral sign. So we have 2r squared times the integral from minus pi over 2 to pi over 2 of cosine of squared theta d theta. Now this integral is very straightforward. So remember your double angle identity for cosine. So remember cosine of 2 theta is going to be equal to, what is it? It's going to be 2 cosine squared theta minus 1. So we can rearrange this equation so we can get cosine squared theta is going to be equal to 1 plus cosine 2 theta all divided by 2. So we can replace that here, so we can just use the backwards chain rule on the cosine 2 theta term. Alright, so that means the area of the circle is going to be 2r squared times the integral of minus pi over 2 to pi over 2 of 1 plus cosine 2 theta all over 2 d theta. Alright, so our 2's will cancel from one another. So we have a is going to be equal to r squared times the integral from minus pi over 2 to pi over 2 of 1 plus cosine 2 theta d theta. And then we can integrate directly these two terms. So that means a is going to be equal to r squared times the antiderivative of 1 is going to be the variable of integration, and then the antiderivative of cosine is going to be sine, and then we also need to take into account that 2 by dividing by it. And then we need to take our limits as theta goes to pi over 2 and as theta goes to minus pi over 2. Alright, so what is going to go on here? So that gives us what? So we have upper limit pi over 2 plus 1/2 sine. So when we plug in pi over 2 here, we just get the sine of pi minus the lower limit is going to be minus pi over 2 plus 1/2 times the sine of minus pi. And then what does that give us? So pi over 2 plus, well, the sine of pi is going to be equal to 0. And then minus pi over 2, sine of negative pi is also going to be 0. And then we have this pi over 2 minus negative pi over 2. So pi over 2 plus pi over 2 is going to be pi. And what do we get here? That means we have r squared times pi. And of course, that is the same as a is equal to pi r squared, which then proves that the area of a circle of radius r is going to have this area, pi r squared. And of course, since you can transform a circle pretty much in any direction, it doesn't have to be centered at the origin at all. The area formula is going to be preserved as long as you don't stretch it or shrink it or puncture it or any crazy things like that into an ellipse or something. This area formula is still going to be the same for any general circle, no matter where it is. And that is how to prove the area of a circle using trig substitution and integration.